Hi everybody, welcome back to the channel. In this video we're going to take a look at a couple more examples dealing with a chain rule, and we're going to build it up and get a little bit more complicated as we kind of continue to add more layers. So to start out, let's go ahead and take a look at an example that looks like this. In fact, in the last video I included this as a possible option as an example, but we didn't actually look at it, and so let's go ahead and refer back to that. So this says e to the 7x squared plus 3. And I'm calling this h of x just so that we don't get confused with f and g notation, because what I've been using is f as the outside function and g as the inside function. So trying not to call this f or g just so that doesn't get confused with which one's the outside, which one's the inside function. Okay, so I will say that a lot of the times when you have parentheses in a problem, it can be a little bit easier to identify the outside function and the inside function. When you have something like this that has an e, or any kind of an exponential like this, it can be a little trickier to see outside and inside functions. The inside function is going to be everything inside of the parenthesis, or inside of the exponent, which you could put parentheses around, but we don't usually put parentheses there, so it can be a little bit deceiving. Just keep an eye out for that. So right here, if we're trying to find h prime of x, that's our goal, we can take the derivative of the outside function. So let me just kind of set this aside for a second. F of something, the outside function, is going to actually be e to the power of something, and then g of x, which is the function on the inside, is going to be 7x squared plus 3. Okay, so again, just good to identify the outside and the inside functions so that we can say that, remember the chain rule says that when we take the derivative of the whole thing, it's supposed to look like f prime of g of x times g prime of x. So just good to identify what's f and what's g here in this case. Okay, so for h, we have the outside function as e to the power of something, which we know what the something is on the inside, but the derivative of e to the something is e to the something. So this right here we could have as our f prime of g part. And then what goes in the parentheses, remember, is just the input of whatever we had for the original function in the first place. So we just kind of copy and paste 7x squared plus 3 up there in the exponent. And then down on the main level, not up in the exponent, but down on the main level, we're also supposed to multiply by g prime of x. Okay, so g prime of x is just the derivative of whatever's on the inside, which on the inside is 7x squared plus 3. So the derivative of the inside is 14x. And you could say 14x plus 0, because the derivative of 3 is just 0, but you don't need to write that. I would recommend putting this in parentheses. I know in this problem with just a 14x, with just one term, it's not really needed to put that in parentheses. But if this was, let's say on the inside was a 7x squared plus 3x, then the derivative of the inside function would be 14x plus 3. There's a binomial there, and that's got to all go in the parentheses because that's all being multiplied by the first term. So I think just as a good practice, I think it would be helpful for you to put that g prime, the whole thing g prime of x, in parentheses, just to kind of start creating that habit, so that we multiply by the entire g prime of x there. Okay, there's not really much you can do to simplify this because you have an exponential function and 14x, which is a linear function, or kind of almost like a polynomial. Could be a polynomial if it's more complicated, but you can't really combine those together. So that's the best we can do for h prime of x over here. All right, we're going to go ahead and take a look at one other example. And in this example, we're actually going to have a situation where we don't just have two layers, an f and a g, but where we actually have three layers. So let's kind of set up a function of what would this look like. Let's say we have an original f of g, but it's not g of x, it's g of, I'll call it p of x. So there's actually kind of three different functions in there. And the question is, how could we deal with that if we're taking the derivative? So what would be d over dx of that thing? Okay, we've only dealt with two layers so far, and we want to think about kind of peeling back one layer at a time. So earlier when we had f of g and we were taking the derivative, notice that what we ended up with had both an f prime in it times a g prime, and then you just got to be careful about what the inputs are into those functions. Now we don't just have an f and a g, now we have an f and a g and a p. We're actually going to end up having 3 different derivatives, but again, remember, it's not a derivative inside of a derivative, it's derivatives being multiplied together. So if you think about what this would look like to kind of go one layer at a time, we would first look at the outermost layer, which is f, and take the derivative of f. But remember, it's not just f of x, or I should say it's not just f prime of x, it's f prime of g of p of x. We just kind of replace, copy and paste the input function that's there. Then we would multiply by g prime, but it's not g prime of x this time. Now it's g prime of p of x. And then we still don't have a p prime yet, that third function, so we also need to multiply by a p prime of x. And you can imagine what would happen if we had 4 different layers or 5 different layers, which that gets pretty complicated, pretty big and complicated. But if there were 5 different layers, then you would basically have one derivative times another. You'd end up having 5 different derivatives multiplied together and then just copy and pasting those inputs. Okay, so that being said, let's go ahead and take a look at an example of a function that has 3 different layers. Again, I'm going to go ahead and call this h of x just so that we're not confusing f and g. Okay, and it's going to look something like this: the sine of e to the x squared plus 1. Okay, so after you've practiced this a bit, I hope that you could look at this and see 3 layers pretty quickly. The 3 layers that are here are, you have the sine function, you have the e function, and then inside you don't just have an e to the x, you have an e to the x squared plus 1. So that x squared plus 1 is kind of your third function there. Okay, so if we called this something like f of g of p, like we did in the last illustration, this would be our f function, our e function, and then our p function right there. And if we're looking for the derivative of this whole thing, we're just going to go one layer at a time. So the derivative of the outermost layer is the derivative of a sine. That's a cosine. Okay, cosine of what? Well, remember, just copy and paste everything that was already inside. So e raised to the x squared plus 1. Okay, now take a derivative of the next innermost layer, and if you want to label these, you're welcome to label these. This part right here is f prime of g of p of x. Need another parenthesis. Okay, and then we need g prime, which is the derivative of e, which is just e. E raised to the power of, and then copy and paste what was ever inside of there. And this g prime right here is g prime of p of x, because e to the x, or e to the something, is its own derivative. Now we still need to multiply by the innermost function, which is the p of x function. We need to multiply by the derivative of x squared plus 1. We need to have an extra 2x on the end. So again, I think having a structure in mind for how to be able to set these problems up can be really helpful. Sometimes you can go ahead and simplify this, but again, in this problem, I don't think there's much you can do. We have a cosine, we have an exponential, we have a linear function. Those don't really combine together very well. So that's as good as you can do to be able to write this. Okay, so just really something to keep in mind when you have a chain rule is, where are your different layers, and really, can you break it down into the outermost layer, and then once you've handled that derivative, then move into the next innermost layer, and then into the next innermost layer. But again, remember, you are multiplying derivatives together and then copying and pasting the inputs from those original functions into in as the inputs into the derivatives. Okay, so a couple other examples here for you to take a look at. I hope this helps you, helps kind of make sense of the chain rule. This does take a lot of practice. I would highly recommend going and getting a lot of practice with this. But good luck with that. Hope you've enjoyed the video.